Hi guys, this is Mrs. Gastler, and in this video we're going to be talking about conservation of energy. So to begin with, we're going to be talking, let's start off with the law of conservation, that's an S, of energy and what it says. First off, nobody wants to write that out again, so we write CE. So whenever you see me write CE, I'm talking about conservation of energy. And it says that in a closed system, the total amount of energy is constant. Okay, constant. So a closed system, we mean there are no external forces. So that means that there's nothing acting on it from the outside. Any forces that are happening are from objects that are included in the system. So if there's any objects that are interacting with the system that are not included in the system, then we're not talking about a closed system. And if that happens, if we're talking about an open system, in an open system, the total can change. Okay, so that's kind of the opposite here. So if we're talking about an open system, then the total amount of energy could change. When we say the total amount of energy, what we're talking about is all of the kinetic energy plus all of the gravitational potential energy added together. Okay. Because we're only talking about mechanical energy here, then that's the kinetic energy plus the potential energy. And it could be gravitational or elastic potential energy, which we haven't really talked about yet, but that will be added in there later on. And so those energies could be in there as well. This could be elastic or gravitational. Right now, you're just going to have to worry about gravitational, which is a nice introduction. We'll add elastic in there later. Okay. And by constant, we mean not changing, right? Okay. In middle school or physics first, if you've had it already, this was probably said, you may have heard this as, energy can't be created or destroyed. But that doesn't mean we can't move it from one place to another or change it from one type of energy to another. And so there's a bunch of different ways that we can show this. Sometimes in physics, we talk about these things called LOL charts, which is my least favorite thing. Actually, I really like LOL charts. I just don't like calling them LOL charts because that sounds silly. What an LOL chart is it's this. Okay, see LOL. This is a bar graph. And this is a bar graph. And this is a circle where you write what's in the system. So you would say, it's Earth. Or it's a block or something like that. Whatever's in the system, you would write that there. And then over here, you would say kinetic energy and potential energy and whatever kind of potential energy is. And you might say, well, I had a little bit and then I had a lot and now I have a lot and I have a little bit. And you would show the energy changes. And if any energy was added or came in, you would show that with an arrow. Arrows to show change like this. Okay, but I didn't actually add any. So maybe there's some, I don't know, maybe there's some extra kinetic energy like that. Okay, so the total change, something like that. And that's what we do to show energy changes. This is an open system now. Now that I included some added energy entering the system. Okay, so those are LOL charts to show energy changes. Okay, so that's something that you might see. But what we often do with the conservation of energy is we use it to solve problems. So we're going to solve a problem, okay? And so this is my example problem. If you want to take a moment and pause to write this down, that's probably a reasonable idea. And I'm going to switch pen colors to, I don't know, is this a different color? I can't tell. Maybe it is, maybe it isn't, and that's okay. All right, so we got a 1,200 kilogram car. It's going 31 meters per second. When it reaches a ramp, if the ramp has an angle of 12 degrees with the horizontal, how far will the car go before it stops? A note here, you could totally use kinematics and some old school things you know about physics to be able to solve these problems, but energy is a better way to go. And so I'm going to use the conservation of energy to solve this problem. First, I'm going to draw a picture, though. Here's my ramp. And here's my car, okay? And here it's going 31 meters per second. And then it's going to go up this 12-degree thing, and it's going to come up here, and it's going to stop. And the question is, how far does it go, okay? Before it stops. And so it looks like I'm going to have to do a little bit of trig. Okay, so conservation of energy. So here's my initial, and here's my final. So my total initial, wait, I didn't write that over here. Let me go back. Total energy is constant. What this means is that the total energy before is equal to the total energy after, okay? And then I can replace that with whatever I have before and whatever after. So K initial plus U initial equals K final plus U final. And then you can just solve for whatever you need. And that's what we're going to do. E total initial equals E total final. Okay, so initially I have kinetic energy, but I don't have any gravitational potential energy. And finally it stops. Okay, and so I don't have any kinetic energy, but I do have some gravitational potential energy. Okay, and so the question is, how far up the ramp does it go? I'm going to redraw a second triangle here because this H is what I'm going to have, but this is what I'm looking for. So I'm going to make that an X and put a question mark there. And this is at 12 degrees, okay? And that's going to allow me to put that together, okay? So and I'm going to put an F there. All right, so kinetic energy is 1/2 mv squared. And gravitational potential energy is mgh, okay? Now, it does tell me the mass of the car, but if you notice, m is on both sides here, so I'm just going to cross m out. Goodbye, m, okay? So I have 1/2 v squared, and I have g, and I'm going to replace h with something. So h is over here, but I need x. So let's see, the hypotenuse, then the opposite, that's sine, right? Sine of the angle equals opposite over hypotenuse. And I want the hypotenuse, so I'm going to have h sine theta equals opposite. So h equals opposite over the sine of the angle. So no, I don't want h. Yes, I do want h. Wait, hang on. I switched up my h's. That was dumb. Okay, let me make this a capital H. There we go. Okay, now it makes more sense. Okay, so I want x. So x is this h Okay, now I've gone and confused myself. Yeah. Okay, I'm just going to leave this over here for now. Okay, so MGH. Okay. And H is what I can find. I know V, I know G, and I know 1/2. Okay, so let me solve this for H. So H equals, so this is X equals H over sine theta. Yeah, okay. I've got myself back here. X equals H over sine theta. And then I'm going to put this H right there. There we go. That's what I'm going to do. Okay. So 1/2 V squared over G. Okay. So now I can put my numbers in. I could put my numbers in here, or I could put my numbers in there. Let me go ahead and put those in here. So 1, and let me put the 2 with the G. So this is V squared over 2G. Okay. V squared would be 31 squared over meters per second over 2 times 9.8 meters per second squared. And does my calculator work, or is this one dead? This one's dead. Wouldn't you know it? I'm here with a calculator without a calculator. And I only have this right here. Okay, so 31 squared. Come on, calculate. 31 squared, 1 squared, divided by 2 times 9.8. That is 49.03 and some other numbers. And that's going to be meters. Okay. So that's what I'm going to put on top, 49.03 meters. And I'm going to divide that by the sine of 12. And I got to make sure that I am in degree mode, which I am. Okay, so that is divided by the sine of 12. And I get 200. Oh, that's a big number. 235.8 meters. Okay, so that is how far it's going to go up there. Now, this next part of the question is a fun one. So sometimes kinetic energy, and so this where did it go? This law of conservation of energy applies in a closed system. It's the total amount of mechanical energy. Now remember in that diagram we drew, we had these other types of energy called non-mechanical energy, which included thermal energy. Now when you rub your hands together, some of that kinetic energy that you have in your hands moving turns into thermal energy, which warms your hands up. Not mine, because my hands are freakishly cold. But some of that kinetic energy gets lost. Some of the gravitational potential energy gets lost. And so sometimes our LOL chart might look like this, where we have some kinetic energy and some potential energy in our system. And that energy might get lost. And so we end up with something that might look like this. Okay. And this would be an open system too. And so we can think about what happens to that lost energy. And so it would look like this. So we will be talking about some of the energy